We've only scratched the surface of molecular orbital theory. For diatomics, we've only used examples where the two atoms are the same. If they're different, the atomic orbitals start at different energies, and the diagram looks significantly different. Now, molecular orbital theory applies to molecules with more than two atoms as well, and it can explain a great deal. It may even help us in understanding the idea of resonance. When we draw Lewis structures, we draw electron pairs that are localized, either as a shared pair specifically between two atoms or a lone pair on a specific atom. This suggests that the orbitals that the electrons reside in are also localized. But in molecular orbital theory, the molecular orbitals are not confined or localized in one place on a molecule. This can help us with the idea of resonance. To go from the left hand to the right hand structure, it would appear that a lone pair on the right atom ends up as a shared pair, and a shared pair in the double bond ends up on the left atom. Resonance with localized structures makes it seem like the electrons just go back and forth, but molecular orbital theory offers a different explanation. The central sulfur is sp2 hybridized with one leftover p orbital. This p orbital can mix with p orbitals on the oxygen atoms to form three molecular orbitals as shown in figure 6.27 from the textbook. In the bottom orbital, the signs and therefore the colors line up. This is a pi bonding molecular orbital, but it is spread out or delocalized over all three atoms. One can then think about one pi bond delocalized over two locations, or half a pi bond on each side. This is consistent with a bond order of 1.5 that we concluded when we first talked about resonance. We also found a bond order of 1.5 between the carbon atoms in benzene. We show the two resonance structures on the left. Notice that where there is a double bond in the first structure, there's a single bond in the second, and vice versa. Sometimes the structure on the right is drawn, where instead of discrete single and double bonds, a circle is shown to suggest the pi bonding is delocalized. But how can that be? Remember that the pi system comes from the leftover p orbitals on the sp2 hybridized carbon atoms. Looking at it this way, you can imagine that, for example, the atom on the front right can pi bond equally with the atom on its left and the atom behind it. The three pi bonds would not be localized but spread out over 6 locations. Sometimes this pi bonding system is shown like this, with a donut of electron density above and below the ring of carbon atoms. Now, the situation is more complicated than we're letting on, since if you mix 6 atomic orbitals, you should produce 6 molecular orbitals, and we're only showing 1. We'll save that complexity for a later course. The point is that molecular orbitals allow us to delocalize bonds over multiple locations, and perhaps give a better picture of fractional bond orders from resonance.